Hey, everybody. I think I'm on the, okay, cool. Make sure I'm in the camera there. Good morning. It's really nice to be here today. I'm very proud and humbled to be at this event and share a little bit about the project that I'm working on called Aleo with you. So the quick TLDR is Aleo is a platform for private applications. We're going to talk about what that means throughout the course of this talk, and I'm the COO. But the first thing is we're going to see if the slides will move forward. And they may not be, so. Okay, so that was the first thing. The second thing is we have to address something right up front because ZK EVMs, all the rage recently, lots of exciting announcements, and understandably so. There's this question of like, can we use zero-knowledge cryptography, which, by the way, I should have mentioned that Aleo is a project that's leveraging zero-knowledge cryptography quite heavily. So can you leverage zero-knowledge cryptography to build a better EVM effectively? So is Aleo a ZK EVM? No, it's not a ZK EVM. But what is a ZK EVM? At first I thought I knew what that meant, but actually Vitalik, his recent blog post, he was just up here, but his recent blog post, it inspired me to change these slides a little bit because I learned from that blog post that the definition of a ZK EVM is a little bit broad, right? So it could mean a lot of different things, right? So this chart is not from Vitalik's blog post, it's from another great post that I've linked below. But you can see there's like the definition on the far right side of what the EVM or what Ethereum, the computing model of Ethereum kind of looks like. And you kind of have all these increasingly distant, different projects that have implemented what people term as ZK EVMs in kind of different ways and increasingly distant in terms of compatibility. Although I would say, in addition to you have the arrow on the bottom that goes to compatibility, I would also put an arrow that ran the other way about performance, right? And so the TLDR is, at least today, so as far as we know, the closer you try and get to a ZK EVM model that emulates exactly the Ethereum model, you pay a quite heavy penalty in performance. So that's why we at Aleo decided to build a new model from the ground up with this exact use case in mind, a ZK VM. And so the way our model works, and I'm going to go through all of this in detail in this talk, so don't worry, is we have a high-level language called Leo, which compiles down to an intermediate representation called AVM instructions, which get turned into AVM opcodes, which then get synthesized into what's called R1CS, which is effectively the stuff that proofs are made of. And okay, so why is this even a hard problem? Why are we sacrificing, why can't we just replicate the EVM exactly? And by the way, I'm going to liberally steal many other people's great insights throughout this presentation, but I will cite them. And this is actually a quote from an article written by a gentleman named Gautam Botral, who works at Consensus. And the TLDR is that the thing that the EVM reasons over are 256-bit words, and the operations there are bitwise arithmetic and Boolean operations. Proofs, what is a zero-knowledge proof? Well, it's a field element, or it's some group element of a field, which is typically a cryptographic field like this elliptic curve that I've shown there. And what is a program in that model? Well, it's a circuit on the bottom, encoded as a polynomial, defined over this field, right? So these are two very, very different things. And typically when you try and translate that into the world of a regular computer program, as Gautam points out, typically the blow-up is quite large. In fact, there is actually already some research that shows you can build effectively a CPU inside of a zero-knowledge proof. It's called TinyRAM. I highly encourage everyone to look it up. And basically, roughly speaking, the blow-up factor of any program is 10,000x in terms of the number of constraints, as opposed to if you just implement the program step by step. Okay, so this is kind of another way to say it. So this is the challenge here fundamentally is like you have an idea for a program, you want to write it in some high-level language. It's like I want to prove that I know the sum of two numbers, kind of a silly program, but let's just go with it. And so you write it out in high-level language, and then what Leo and the AVM does is compiles it down, and it manages this problem of basically efficiently translating between the world of zero-knowledge cryptography, or the cryptographic world where things are all group elements defined over elliptic curves, and the world in which the program actually needs to be evaluated, what's actually being computed here. And to do that efficiently is why, again, we built our stack from the ground up. And this is why it's very difficult to do this this is why there's all these different flavors of ZK EVMs. So again, this is kind of another model of how Aleo works, and we'll go through this in a little more detail. But the point I want to make quickly is, so today we have Leo that compiles to AVM, and then we have SnarkOS, which is basically our layer one, where we have validators that also serve as verifiers that can verify transactions were computed correctly. And the point that I want to make here is that, okay, so we have Leo that targets the AVM, but maybe in the future we could have other languages that target the AVM too, or even potentially a transpiler that targets Leo or the AVM directly. So there could be a world in which you could write Rust or Solidity or some other language, and maybe through some transpiler architecture, you can just basically end up still being able to do all this. And so this is an interesting future direction. Very similar to, actually I'm going to go back, very similar to, I guess if you go back to the definition of the EVM, on the far left, this is what Aleo could potentially someday look like. But okay, so now back to the question, is Aleo a ZK EVM? Maybe, although I still would say not really, right? And the point is, it's like, okay, what's the whole point of a ZK EVM? What do we care about here? Why is the EVM important, right? The EVM is important because we want to be able to compute, we want general programmability on chain, right? And so what I define Aleo as is a platform that uses a ZK VM. Like again, the E part here I think is extraneous because what we ultimately care about is computing programs on chain using zero knowledge. So now I'm going to tell you a little bit about Aleo after this quick kind of digression. And the first thing I want to acknowledge is that Aleo is not an Ethereum killer, it's not a Bitcoin killer, it's not a Solana killer, it's not anything killer. Aleo represents a step along a path that had many prior steps before, and I think it doesn't get acknowledged often enough, especially in the modern world of crypto conferences, that for like 40 years there were all these failed projects that tried to build digital money and failed, but ultimately inspired Bitcoin, right? And Bitcoin, the key insight of Bitcoin was actually not cryptographic at all, it was crypto-economic, right? This concept that you could have miners, if you build an incentive structure a certain way, it aligns the incentives of the participants of the network and the miners and everyone, and then the whole system works trustlessly and permissionlessly. And so Bitcoin, that insight kind of inspired a lot of different directions from that same kind of turning point. And Ethereum, similarly, the insight that Vitalik and others had was, okay, well, we have Bitcoin and it's really cool, but it's not as powerful as it could be. Imagine if we took a computer and we put the computer on chain. And again, so we had that, if we go back to 2015 and 2016, 2017, you see all these different projects that take that idea and run with it, right? And so this is kind of its own direction, this on-chain VM model. And Aleo implements a model which is based on some research that was authored in 2018 called Zexi. And the idea of this was to try and combine some of these past approaches and accept some trade-offs, but to be able to have an off-chain computing, basically where you compute program transitions off-chain and then verify them on-chain. So we view this as a step in a different direction that gives you some kind of cool new powers. So we're going to talk about that through the rest of this talk. And maybe I'll just highlight to me the two best parts of this potentially is that, again, as we all know, on Ethereum you need gas. And why do you need gas? To make sure that no one can force the EVM into an infinite loop, right? So gas is there to make sure that effectively no one can DOS the system. And that's because every node is executing every single transaction to verify that it's correct. Now, in the world of zero-knowledge cryptography, as Vitalik pointed out in the last talk, is the beauty of this is you can cryptographically prove a statement without revealing why it's true. And if you accept that proof, well, the only honest verifiers will always accept that proof as valid. So therefore, you don't need to re-execute the entire instruction of the entire program. So that's really cool. So it's more efficient in that way. And also, in the additional thing, and we're going to talk more about this later because I think this is really an underrated insight, is that you have unlimited program runtime. So actually, a quick pop quiz. I don't know if anyone knows this, but does anyone know the stack size for the EVM offhand? Okay, so it's 1024. So the stack size of Ethereum is 1024 elements, right? So theoretically, you can write a smart contract that would overflow the stack size on Ethereum. So there's a limit, effectively, and I don't think for most programs it's of any practical importance, but the important thing to note is there's a limit into what you can do here. So in the Aleo model or in the ZK VM model, you don't have this limit because you're running a computation entirely off-chain. So you could, I don't know why you would ever do this, but you could do a protein folding algorithm for years, and at the end, you can come up with the result and then present that as a proof, and then that proof would be as valid as any proof. You don't need to do it within the window of a block. Cool, and then I have this kind of chart here which shows how I view Aleo as kind of a mishmash of something what Ethereum's trying to do and Zcash. Architecturally, and we'll go through this in the next slide, architecturally I think the way to think of it is a little bit closer to Zcash. In fact, I'll just jump ahead. It's a bit of an extension of Zcash where if you think in the Zcash model, you have records And these records basically are the fundamental unit of data on chain. And then the way state updates happen is people prove they have ownership of a record, that the record exists in one of these specific data structures, and that they have the key that allows them to spend the record, and then you can basically use that to create a system of payments, right? So there's a transfer. This is exactly how Tornado Cash on Ethereum works as well, by the way. And Zexy, the model, is that exact same thing, except instead of just payments, there's this additional parameter that a record has, which is what program ID. And this opens up the door to being able to define basically user-defined, or you can have user-defined predicates or developer-defined predicates. So instead of just I pay you, you pay me, we can have more complex logic in there and have the proof represent that. So just quickly here, how this works is you do a one-time setup of the system in the beginning, you generate all the parameters you need to prove and verify, and then you have a prover, and we'll talk about the different parties in the system in more detail over the following slides. You have a prover, basically takes some public state, some private state, a user signature, generates a proof, and then submits that proof to the chain, and you have a separate party, which are the validators or the verifiers on chain. They verify it once and then update state as a result. One thing to quickly note, which I'll mention a couple more times in this talk, is that the prover can be you or it can be someone else. So it's a bit flexible, and depending on what trade-offs you want to accept. Do you want to share information about what you're doing with a third party, or would you prefer to keep that private but potentially do it in a slightly less efficient way? Okay, so this is maybe just a little bit fancier way to visualize that. So once again, we have developers in our system, and the point, just like in Ethereum, you have developers deploy smart contracts. In our model, you have developers that deploy programs to an on-chain program registry. So we have our on-chain registry, developers deploy a program, and that program is the compiled AVM bytecode that corresponds to the logic that they wrote. And now provers can, once they receive a transaction, a request from a user, or again, you could be the prover yourself, you take that AVM bytecode, you take the initial parameters generated during the setup, you synthesize all the information you need to generate a proof, you generate the proof, that gets wrapped into a transaction, and then that gets submitted on chain. And then state updates occur. Okay, so actually, it's kind of similar to the way that rollups work. I think a lot about this. I think there's this concept now of modular blockchains that a lot of people have talked about. And in a rollup, it's kind of the same idea, right? You're separating the execution from the settlement, effectively. And so this is exactly what we do in Aleo natively. So in Ethereum, you have developers or users, and they're submitting intents to rollups, basically, signed, hey, I want to transfer from A to B. And then, yeah, I'm stealing some of Adrian's lines, so sorry about that. So anyway, the rollups execute these intents, and then the validators, the layer 1 validators, verifies that these intents were executed correctly. And this is the exact same model that we follow, although, again, it's a different architecture, built from the ground up to be slightly more efficient. Okay, so I kind of went through all this. I guess maybe instead of going through this all again, let me just say one thing quickly about what makes the architecture different than something like Ethereum or many other chains. Is that I mentioned a minute ago, when you deploy a program, you deploy to a program registry. So what that means is there's effectively a namespace that exists on chain that's tracked by all the validators, because this is exactly how you know what program you're interacting with. Because if I just give you a proof, you don't know what program it is, it's impossible to reason about a state update. So this is kind of an interesting thing and opens up a lot of doors to potential applications. So you could have a namespace and put anything inside the program ID. So this is in addition to being useful for programs, could also be useful for identity applications or other things. Yep, okay, and so we have this concept of callers and provers, where if the caller calls a prover to execute some function, again, in the real world, like these are computer science concepts of just we're separating these two agents, but in practice, you could be both the caller and the prover. You could synthesize, there's no reason why you couldn't synthesize your own proof yourself. And that's, I think, very important, because I think one of the, it implies decentralization, but I think decentralization is a very worn out word in the space, but I think more importantly, it implies permissionlessness, right? So that you don't need to ask permission for anybody to deploy a proof, which means there's a lot more opportunities to potentially compose and combine things. Okay, and then we talked about validators and they verify proofs. I think that's probably enough to say about all that. Okay, so this is what it looks like in summary. So let me just restate it all again from the beginning. So Aleo is building a new layer 1 blockchain using a proof of stake architecture based on a variant of hot stuff, which for any of you are familiar with that consensus algorithm. And it uses a computing model based on Zexy, which is a ZKVM. And in that model, it's defined by off-chain computation featuring unlimited runtime, where transactions are proofs, and these proofs are then submitted on-chain validators verify these proofs are correct, never have to re-execute them again, and then effect state updates, all in a way that preserves perfect privacy. So this is called decentralized private computation. This is the term from the 2018 Zexi paper, which talked about this primitive. And I think this is extremely exciting because for the first time you have this permissionless system where you can deploy programs and interact according to the logic of those programs privately on chain. And so we're really excited about this potential paradigm. Okay, so I'm going to go through I guess in more detail. I've talked a little bit about a lot of these points, but like, why does this matter? Who cares? Like, what's good about this? Okay, so the first is, I think, at this point, we've all been to enough Ethereum meetups that we know that scalability can be challenging on Ethereum. And one of the reasons why scalability is challenging is that every single node has to re-execute every single transaction, right? And this is why rollups are oftentimes looked at as a really promising architecture because it separates these two things, right? So when you separate execution from settlement, you get greater scalability and efficiency. So yeah, this is basically, I guess, maybe a picture that communicates that. You guys check the slide real quick. Oh, there we go. Let me go back. Okay, cool. One thing I just wanted to take, and I know there's a typo on this slide, I apologize. One thing I wanted to just take a digression and talk about is Aleo is a proof of stake blockchain, and I was talking about efficiency a second ago. I already talked enough about how when you're a prover, you execute a transaction, it only needs to be verified once as opposed to forever for all time by every node. One of the things that we have implemented, which I think we're the first team to implement, are frost signatures for our consensus algorithm, and this is what validators use in the process of consensus to sign basically that or validate blocks. But users or developers can also take advantage of this paradigm, and frost is basically a threshold signature scheme using Schnorr signatures, which recently got integrated or is being integrated into Bitcoin. So for those who aren't familiar, Schnorr is a really nice, efficient signature scheme. If you saw my prior talk on Thursday, you'll know that Schnorr is actually a zero-knowledge protocol called a Sigma protocol. And but anyway, the point here being that it's much more efficient to aggregate several signatures together and cheaper. And so this is a way in which you can do things like multi-sigs in a way that's much cheaper in terms of constraints than you could do in potentially other systems. Okay. Oh, the other thing that I'm excited about, we could do a whole presentation on all the really interesting directions that zero-knowledge cryptography as a whole is developing, and kind of the ways in which this is getting better and better and better every single year, thanks to the contributions of many people, including some of whom are in this room. But we use a proof system called Marlin, which I probably should have mentioned a minute ago. Marlin is a universal zero-knowledge proof system, which means that any logic that you can think of, you can prove up to a certain size. So this is a relatively recent phenomenon, I guess since the post-2019. And originally Marlin did not integrate any kind of lookup table, which is a feature of another proof system called Plonk. And so one of the things we're very excited about with what we're doing is we're integrating kind of the best of both approaches here, and we're taking the lookup tables from Plonk and we're integrating them into the Marlin proof system to get much greater efficiency than you could in another context. And why is this important? I guess for those of you who aren't familiar with Plonk and like why lookup tables help a lot. So there's certain I mentioned a while ago, there's like computers and how we reason about programs and bitwise, arithmetic and integers, and then there's cryptographic elements. To translate between those things for certain operations is really expensive. For example, Kachak hashing in Ethereum is very costly to do inside of a zero-knowledge proof because it's two different things. But you could implement a lookup table and make these. You could take the cost way down. So you can basically use it to pre-compute expensive functions, and then have that be much quicker or cheaper to prove. The other thing that this gives you is batch proving. And this is actually very similar to how rollups work. In Aleo, every transaction can consist of 64 separate state transitions, and these are batched together in a single transaction. And kind of the cool thing about the model that we have using Marlin is you can batch these together in a way that the cost increases sublinearly with the number of transactions. So, you have a single transition, costs, X amount. And then as you go up and higher, closer and closer to 64, it increases sublinearly. So it kind of really it encourages, batching of things together and makes it even cheaper for the prover to ultimately compute. And I think the crossover point is basically a 4x reduction in prover time once you reach 4 transitions. Okay, moving along. So again, I wanted to go back to program runtime and why this is potentially cool and important. I gave a couple of examples, but another example that I think is really cool that no one has talked about before is using ML potentially to define some program logic. So you could imagine a world in which again, and actually backing up, can you do ML on Ethereum, like a linear regression, for example? And the answer is, well, it's quite expensive, again, because of the gas limit that we talked about. But because we have an unlimited runtime here, ML applications are actually fine to do in ZK. And in fact, there's a lot of really cool, interesting applications. I mean, one that we kind of played with or talked about as a toy is using potentially an ML algorithm to define a bonding curve, right? So if you think about, you take prior trade data, you run a linear regression on it, you can maybe define and publish like some new parameters around some type of bonding curve where you could trade assets against. So this is like an example of an application that is really hard or even impossible to do in the model of the on-chain computation, but is relatively trivial to do here. Cool, and yep, okay, I think I hit on this enough. The other thing is privacy. Privacy is an interesting topic in this space because a lot of people feel very differently about it. I think for many applications at scale, privacy will be absolutely essential. I mean, if we think about the model of just blockchains in general today, it's actually shocking how transparent they are for most financial use cases. I mean, if I send somebody USDC and they've given me their address, not only do I know the content of their account, I know every single interaction they've ever had with anyone, and then recursively can figure out all of those people's interactions in the state of their account, which is very, very unlike the traditional financial system. And I think as all of us in this industry think about bringing this to the world, it's incredibly important to keep in mind that privacy is going to be a really, really critical piece, especially for financial data that people really want to protect. And so I think it's why we built this in as a first-class citizen within our system. And importantly, in Aleo, and this is maybe a distinction from Zcash and actually from some of the lessons learned from that experience, in Zcash, privacy is opt-in. So and this is actually similar how to Ethereum and Tornado Cash work. So the Tornado Cash, actually let's use Tornado Cash because it's Ethereum related. So Tornado Cash, you have an anonymity set, which is basically everybody who's transferring funds on that platform. But that is a tiny, tiny fraction typically of all of the funds that get transferred overall on Ethereum. And I guess the TLDR on why this is important is the smaller your anonymity set, functionally the worse your privacy. And conversely, the bigger the anonymity set, the more you can kind of mix things together, the better your privacy. And so in Aleo's model, we have this privacy by default. So privacy by default means every transaction is private. And if you want to reveal certain information, you can. I think I got my slides a little bit out of order. Here we go, yeah. So this is actually some Aleo instructions. And by the way, if anyone's curious about what the syntax or anything looks like, this talk is not a developer workshop. This is more of a high-level talk, but we have on GitHub a bunch of examples, what Aleo instructions look like, how to use them. But anyway, this is just a quick screenshot. So you see we have two inputs. One is public, one is private, and we can also output public and private values. And like I said, this is how you as a developer can define what is private and what is public in your application. And you as a user also have the choice to share a view key with different parties if you want, regulator, et cetera. And so I think this is really important. This privacy by default is important because, again, the anonymity set increases the security and privacy for everybody and ensures that this principle you're trying to achieve is actually maintained. Okay. Another thing I'm really excited about here is this concept of approving as a service, which is what we're trying to really encourage and incentivize. And I think as we look at a world in which roll-ups in general across the space are seen as increasingly important and ZK proofs are seen as increasingly the future of computing, you're going to have an entirely new class of infrastructure built around proving quickly and efficiently. It's kind of similar to the current client-server model of the web, where I have a mobile device, and if I'm interacting with some program, typically the way it works is I outsource, I send some instructions to a server which computes something and then it sends it back and renders a result. Similarly, in our model, like I said, we have this option for users to delegate proofs to a third-party prover, And in that model, we imagine there could be provers that are quite performant. And why would they be very performant at generating zero-knowledge proofs? Well, in Aleo, provers can actually generate proofs for the protocol for the purpose of earning some of the Coinbase rewards. So unlike some systems that are proof of stake, it's only the validators that get rewards. In our system, we actually split the Coinbase reward. Some goes to the validators for producing blocks and ensuring that they're doing their job of verifying transactions. But some of it is just paid out to the provers who are effectively doing some work, some proof of work puzzle. And the reason why this is important is because it normalizes the returns for provers. So it incentivizes them to build better and faster and more efficient hardware over time, which then benefits the entire ecosystem, which I might add extends even beyond Aleo. So the way this works is that the Coinbase puzzle is effectively generating a proof. It's not actually a full zero-knowledge proof. It's a polynomial commitment, which is part of the proof production process. But anyway, as I said, the point of this is really to make sure that provers on our ecosystem are incentivized. And we actually had, on our second testnet, we had actually the consensus mechanism we ran in our second testnet back in January was a little bit different. It was more of just a strictly proof of work. And it was a really interesting experience. But one of the interesting things that came from it was that at one point, our network was producing 20,000 zero-knowledge proofs a second, which is an astounding number of proofs if you look at, if you think about like what that means in terms of scale. And I think it really goes to show how powerful incentives are in proof of work systems. And so again, we are not a proof of work blockchain, but we've retained this kind of incentive compatible architecture because we believe that provers are going to be a really essential part of how the future of zero-knowledge cryptography evolves. Okay, and then the last thing is it retains composability. I want to go back here to the concept of the program registry, which I talked about in the beginning. And I mentioned this in one of our talks that I was giving last night, where it's always kind of funny to me to consider that, in Solidity, there's no way to import some program in like a library, similar to how you could do in Python or Rust or many other programming paradigms. You just import, someone else writes a code, writes code for, I don't know, a signature algorithm or, factoring or something. And you don't want to rewrite or re-implement all that yourself. So you want to import this in a single line. You say import X library is typically the syntax. In Ethereum or with Solidity, that's typically not how it's done. And actually, I'm not sure, I don't know of any other language in which this exists for blockchains. Typically, you have to copy and paste all of that program logic and put it in your smart contract. And for Aleo, we are actually enable people to import programs from the program registry directly, and the compiler that we have basically figures out and inputs that it synthesizes those circuits directly into the compiled R1CS of the final program. And the cool thing about this is it retains composability. So you can take what different people have worked on, combine it into something new, which I think is one of the most powerful parts about crypto architectures in general. And then the second thing is you can potentially create a world in which micropayments to the writer or the creator of a library are possible, right? And this is, I think there's many, many examples of open source libraries that are very fundamentally important to the web in general, and the maintainers of those are highly undercompensated given that importance. And so we're kind of excited about this paradigm because we think it's a way where we can change that and make an incentive compatible model for people to do this really important work. Okay, I just told you all the reasons why Aleo is amazing and why zero knowledge is amazing. What is it not good for, you should be asking me. And the reality, and I'm going to use, again, I told you I'd steal liberally from a lot of other people's work. I highly recommend you read Vitalik's blog post about this. I can't remember the title, but it was 3 or 4 ago, where he talks about zero knowledge proof applications. And one of the things that he mentions in that in that blog post, which I entirely agree with, is that it's difficult to create applications that require concurrent access of the same state at the same time. So, Uniswap, for example, is not impossible in this paradigm, but it's also not simple. Like, there's a lot of assumptions that go into it. And maybe this is an example of an application that is better on a transparent blockchain like an Ethereum or Celo or something like that. And this is why I go back to say, and my personal belief is, there's going to be many architectures that are purpose-built for different things at the product or user level. And so you'll have these different ecosystems in the future. And again, I think at the lower levels, different protocols are making different trade-offs. And so this is one of the things that is a trade-off that you make when you're using zero-knowledge cryptography. Now, one of the cool things about cryptography is there's other primitives, one of which Vitalik mentioned in his prior talk, like multi-party computation. I'm sure Adrian's going to talk about fully homomorphic encryption. There's other things, other tools we have in the toolkit that can potentially solve this problem. And we're at the beginning of the potential for this technology, and I'm extremely excited to see how things continue to develop there. Okay, and so I'm quickly going to, I should quickly mention that we had a test net that ran in January. We're launching our mainnet in December. Between now and then, we're running a testnet 3, which is the final kind of burn-in for our network. We just launched last week. The initial phase is focused on developers deploying programs. So if any of you are interested in this, highly encourage you to go to our GitHub at Aleo HQ. You can download all the repos. You can get a feel for what writing programs in Leo and the AVM is like, deploy those programs to chain, and we're incentivizing this process, and we'll be releasing some details in a blog over the coming days. But this is what we consider the first phase of our third testnet. The second phase is where we really open it up to provers. I mentioned a minute ago we have this coin-based puzzle that provers can participate in to earn credits, and this will be the focus of the second phase. So we want people, and potentially, for anyone in this room who is an Ethereum miner who might be facing a situation where your GPUs might not be that useful anymore, you can take those GPUs and prove on Aleo to help earn or to earn coin-based rewards, and then potentially with those rewards participate in the third phase where we have validators and who are, again, as I mentioned, we have this proof of stake consensus. So with the tokens that you've earned as a prover, you can participate as a validator, help construct blocks, and verify transactions. And with that, we'll take from the third phase, we'll go right into our mainnet launch plan for the end of the year. Okay, cool. I want to end, I have 2 slides left. I want to end on and say a couple things because this is an Ethereum meetup, and I want to talk about a couple, and I guess I should say, I myself, even though I'm working at Aleo, consider myself to be a member of the Ethereum community, have been for a long time. And there's other things that I work on and we work on at Aleo that I think are relevant for anyone and in the Ethereum community or beyond. And one of them is zPrize. zPrize is focused on accelerating hardware for zero-knowledge proofs and ZK snarks. So an effort that Aleo is part of, but it also includes 20 different teams from across the ecosystem, including Anoma, many others, Polygon as well. And this is really exciting because I think one of the things that people don't realize about the progress of the web is that one of the big turning points was adding in cryptographic instructions into Intel chips to make HTTPS faster from a human standpoint. So I remember a day or a time when I was much younger that to load an HTTPS website it felt a lot longer than it does today, and that was because these cryptographic operations that you need to perform when you're doing an HTTPS request as opposed to an HTTP request are much more expensive. And when Intel baked those directly into the CPU, that reduced the human time cost tremendously. And I'm hoping, I feel, and you already can see with the number of startups that are starting focused on ZK hardware, that this is the direction of zero-knowledge proofs too. So even though we have kind of this, it's expensive to compute these proofs in kind of the typical complexity model, in real-world human time, you can reduce that time tremendously by advancing and increasing the sophistication of hardware. And we're already seeing the progress. I mean, even in the last 10 years, it's astounding. If you look at Zcash, Zcash transactions used to take a minute or more, and now it's easily sub-second, right? And Aleo, similarly, transactions take sub-second. And with specialized hardware, we can take that even further. So this is an effort I'm really excited about. This is, by the way, I should say a little more about this. So the zPrize is a competition where 70 different teams from around the world are competing to solve these problems that are kind of really important with regard to generating zero-knowledge proofs on different hardware platforms, on servers for provers as a service, on clients, and on mobile phones. So all of the work is going to be open sourced when the conclusion ends in October, and I'm really excited to share a little bit more about it at that time. The other thing I wanted to tell you is I glossed over this in the beginning of the talk, but Aleo relies on ZK snarks, which require trusted setup. And obviously, this is incredibly important because the security of the system depends on the trusted setup. And so this is why we spent a lot of time, effort, and energy to run a setup ceremony. We actually ran 3 setup ceremonies. As I said, our proof system that we use is Marlin. There was one time when we were combining Groth 16 proof systems and Marlin together. And so we actually ran 3 setup ceremonies, one for Marlin for up statement size to the 28th, and then 2 for Groth16, size 2 to the 20 and 2 to the 19th. So we ran a phase 1 for both the Groth16 ceremonies, and we ran just marlin setups only require 1 phase. So the marlin setup has 137 contributors to it, so people from our community, from the Ethereum community, from around the world who participated and generated these parameters. And the Groth16 collectively, both of those other 2 Groth16 ceremonies have over 1,000 contributors each. Why is this cool? Well, there's no reason why anyone else can't use these setup parameters for their own zero-knowledge projects. So it doesn't have to be on Aleo, it can be on Ethereum, it can be anywhere. You can use any of the parameters that we generated, and you can take those and you can build your own circuits without having to redo a trusted setup yourself. And if you want to see, you can see Aleo or setup.aleo.org. You can see all the information about who attested to contributing and get a sense for how, in my opinion, the way to assess the security of these things is how many people contributed. And I'm pretty happy to say that we have the largest setup that I know of in history for crypto. So again, this is something that we view as a public good that we hope, not only do we hope, but we want people to take and use in their own projects. Okay, so if you want to learn more, I've got some links here. So aleo.org is our website, community where we put out most of the announcements with regard to testnet, et cetera, aleo.org/discord. And then we have a Twitter handle. I would encourage you to follow us if you're interested in zero knowledge in general. And thank you very much. I don't know if we have time for questions. Okay, I may have run over, so sorry if I did, but thank you very much, everybody. I really appreciate it.